In today's lab, we're going to be using an air track, which is this right here, which is a device that has air that's forced through it using this pump. I'll turn it on, and when the air is forced through it, it allows this cart to move with very little friction on it, kind of like an air hockey table. Just turned it on, so you can hear the pump, and you can see that the cart moves ever so slightly on the track. Ideally, it wouldn't move at all right now because there would be zero friction, but it would be level. And so I try to level it as much as I can, using a little bit of paper on both ends there, or at least a little bit of paper on this end of the track to try to push it up a little bit. Otherwise, it was slightly angled like this. So there's a small uncertainty, but you can see right now that the cart is maybe accelerating a tiny bit to the right. But it's about as level as I'm going to be able to get it. One measurement of the cart that's important is to measure the width of the sail. That's requested in the lab. And so if you measure this sail's width, it comes out to 10 centimeters. You can see that right here. So we're going to use that. And how we're going to use that is, this is a photocell gate, and this is the timer that goes along with it. This angle here. Okay, so this timer here will record the amount of time that something is blocking these photocell gates. So I'll try to do this so that you can see my hand passing through it, and you can see the timer, I'm hoping, right here. So when I pass my hand through, notice that the timer starts to move, and then it stops when my hand's done. And then I'll press reset, and I can do it again. So my hand was in the photocell gate timer for 0.169 seconds. So this gives me a time interval over which the photocell gates are blocked. And if I know how wide the sail is, I can determine the velocity of the photocell gate by dividing that 10 centimeter width, 0.1 meters, by this time here. So that gives me kind of like an instantaneous velocity of the cart as it's passing through the different photocell gates on the track. That's what we're going to be doing in today's lab, making measurements of that. And from those measurements, we're going to be able to predict and calculate what the acceleration was that the cart experienced. We could do it with acceleration. We're going to be using conservation of energy to determine the final velocity of the cart. And that's from a different part of the lab where I discussed that. But right now, I'm going to be taking the measurements and determining how far physically the cart drops when it's running along the air track. And from that difference in height, I can figure out what the final velocity of the cart should be, given that its initial velocity was 0. All right, there are two stands that support the air track. They're separated by exactly 1 meter, which makes the calculations easier. Underneath one of the stands, I'm placing a block of wood of 2 centimeter height, that's 0.02 meters height. All right, and it might be difficult to see the measurement, but I can tell you it is 2 centimeters tall. So that means that this stand here is 2 centimeters above the other stand, which is 1 meter away. That means for every 1 meter that the cart moves, it drops by 2 centimeters. That 2 centimeters drop per meter is what we are going to use to determine the cart's velocity at any point. So if it drops 2 centimeters in a meter, in a half meter, it only drops 1 centimeter. In 40 centimeters, it drops, 0.8 centimeters. So we can do the math using similar triangles to determine how far the cart drops at each of the placements of the photocell gate. So we're going to measure its velocity as it moves different distances along the track, and for each distance it moves, it drops a different distance. The further it moves, the more it drops, the faster it's going to be moving, using the equations of conservation of energy. All right, so I'm going to back up the computer and show you the measurements of where I'm going to place the photocell gate. The first one, it suggests 0.4 meters down the track. I'll go with that. So notice that my cart right here, you may not be able to notice it, but it's centered at 8 centimeters. So I'm going to place the photocell gate such that it is 48 centimeters away, and I'm going to verify that by, as best I can, by moving the cart. See, the photocell gate is about 7.5 centimeters wide. So if I can put the 48 centimeter mark at about 3 3/4 centimeters, which is right there, then I should be pretty close to having this photocell gate at the 40 centimeter mark, or at least 40 centimeters beyond where this one starts. So when the cart passes through the first photocell gate here, it will have moved a distance of 40 centimeters, and you can figure out what it's dropping, what its amount that it vertically dropped is. It would be 40 divided by 1 is equal to the amount dropped divided by 2 centimeters. And as I said earlier, it should be 0.8 centimeters. Okay, we're going to do this. We're going to do a few trials of this. I'm now going to turn on the fan, or the air, and let the air come out of the holes. And I'll place the cart at 0, which is actually 8 centimeters, and have it go through 48 centimeters, meaning it'll it'll slide 40 centimeters along the track. And then we'll see what its time that it took to get through this cart is here. The photocell gate is here. And from that, we'll determine the final velocity of the air cart, given that its initial velocity was 0 meters per second. So turning on the fan right now. And I'm going to repeat it 3 times. So the first measurement was 0.2506 seconds. Gives us a lot of sig figs here. Keep that in mind when doing the calculations later. 0.2506 seconds. I'm going to write it down myself. The other two should be very similar. All right, I'm about to do the 1.2 meter distance. I realized I was supposed to do 5 trials. I'll do 5 trials here, then I'll go back and do 2 more trials at the other distances. First trial. .1467 seconds. Second trial. .1471 seconds. Third trial. .1470 seconds. Fourth trial. .1464 seconds. I think this is the 5th trial. .1465 seconds. Okay, this is a repeat of the second distance. And we got .1789 seconds. One more of these. .1788 seconds. One of the parts of the lab asks to put a slotted mass on the air track and then to time it, or to do the same thing for one of the trials, just to see if the presence of a mass will affect how long it takes to slide down the ramp. We have to be a little careful here, and I'll tell you why, and this doesn't come up for most students unless they ask me in the lab. If you put too much mass on it, it's going to increase the normal force on this, and it's going to reach the point where the air isn't able to provide a cushion, and then you start getting friction, which is not what we want to have happen. We want to have this be the cart sliding down without friction, so we don't want to put so much mass on that the cart is going to start having friction. We want to have it slide down with more mass on it, but without any friction. Because a lot of the equations we see, mass cancels out. So that tells us that mass should not be a factor. So even this 50-gram mass causes it to weigh down and causes some friction to take place between the cart and the track. So what I did is I took 22 grams of clay, I put about half of it on each side, and I'm going to repeat it at the second distance of 0.8 meters and see if that affects the time. It definitely makes the cart heavier. It's heavier, but not enough that it's going to cause friction between the cart and the air track. So here goes. Right? Cart with mass on it, second distance of 0.8 meters. Let's see what the time it is to take to get through. I get 0.178 seconds. This is the final trial, going back to the 40 centimeter distance. The final two trials, I should say, because we only did 3 earlier. I'm going to finish them off now. It's kind of nice because I actually reset the photocell gate. I moved it to a different distance, brought it back, and tried to put it as close as I could to where it was originally. And so if I get similar times, I know that I did a good job. Things should be repeatable. So when I do an experiment, I should be able to tell somebody else what I did. They should be able to do the same thing and get the same results. It's kind of like what happened here. So let's see if that's the case. 2 more trials at the 0.4 meter distance. Okay, trial 4. 0.2527 seconds. Final trial. Hitting reset helps so I can get a fresh time. There we go. 0.2532 seconds. That's it.